The year is 1903. The world moves at a slower pace than you might imagine. There are no jet engines cutting through the stratosphere, no sonic booms echoing across continents. There is only the gentle sound of wind moving across open fields, and the dreams of those who dared to imagine that humans could fly. Let yourself relax as we explore these quiet moments in history. Each attempt to fly was measured not in miles, but in feet. Each success was celebrated with genuine wonder. Each setback was met with patient determination and the quiet resolve to try again. Let's begin. The Wright Brothers' journey. In Dayton, Ohio, two brothers ran a bicycle shop, Wilbur and Orville Wright. Their days were filled with the simple rhythm of work, the turning of wheels, the careful adjustment of chains and gears. The shop smelled of oil and metal and fresh rubber. Customers came and went. Bicycles were repaired, sold, sometimes built from scratch. But in their minds, the brothers were thinking of wings. They read everything they could find about the experiments of others. Otto Lilienthal in Germany, who glided through the air on fabric wings before his fatal crash in 1896. Octave Chanute, who studied the mechanics of flight with careful precision and shared his knowledge freely. Samuel Langley at the Smithsonian, who believed that steam power might lift a machine into the sky. The Wright brothers absorbed this knowledge slowly, methodically, like water seeping into sand. They began with kites, simple kites, flown on summer afternoons. They watched how the wind moved across the surfaces, observing the subtle shifts in pressure, the way a curved wing could generate lift. There was no hurry in their work, just observation, just patient learning. The brothers noticed something that others had missed. Control was more important than power. A flying machine needed to respond to its pilot, to bank and turn and maintain balance. They developed the concept of three-axis control: pitch, roll, and yaw. Every aircraft that would follow would use these same principles. In 1900, they moved their experiments to Kitty Hawk, North Carolina. They chose this remote place for its steady winds and soft sand dunes. The wind there blew constant and predictable across the Outer Banks. The sound of that wind, the endless whisper of it moving through beach grass, became the soundtrack to their work. They built a small wooden shed to house their gliders and tools. It was a simple structure, offering shelter from the occasional rain, but little else. They slept in the shed, cooked simple meals, and spent their days testing gliders on the dunes. Day after day, they tested their designs. One brother would lie on the glider while the other helped launch it down the gentle slopes. Sometimes the glider would drift smoothly for several seconds. Sometimes it would dip and turn unexpectedly. Each flight, whether successful or awkward, was simply information to be recorded and studied. Between seasons at Kitty Hawk, they returned to Dayton and built a wind tunnel in their bicycle shop. It was a simple wooden box 6 feet long with a fan at one end. Inside, they tested wing shapes by the hundreds, measuring lift and drag with homemade instruments. Each wing shape was carefully measured, the results were written down, and small changes were made. By 1903, they had learned enough to add an engine. They built it themselves, with the help of their mechanic, Charlie Taylor. It was a simple 4-cylinder engine, producing just 12 horsepower. The engine block was cast aluminum to save weight. It ran with a steady, rhythmic sound. They also carved their own propellers from laminated spruce wood. They realized that a propeller was really a rotating wing, and they applied the same aerodynamic principles they had learned from their wing experiments. The propellers were 8 feet in diameter and turned in opposite directions to cancel out torque. On December 17, 1903, on a cold morning at Kitty Hawk, Orville Wright lay prone on the lower wing of their flyer. Wilbur stood beside the aircraft, steadying the wingtip. The engine started with its familiar rhythm. The propellers began to turn, creating their own wind. The flyer moved forward along a wooden rail they had built to keep it straight during takeoff. It rolled slowly at first, picking up speed. At the end of the rail, it lifted gently into the air. Orville held the controls, making small adjustments as the aircraft climbed to about 10 feet above the ground. For 12 seconds, it stayed in the air, 120 feet across the sand. The first powered, controlled, sustained flight in history. When the flyer landed, it settled back onto the sand as quietly as it had risen. They flew 3 more times that day. Wilbert made the longest flight, staying aloft for 59 seconds and covering 852 feet. Not far by any measure, not fast, but they had flown. They had proven it was possible. The nature of early flight. Understanding how these early aircraft flew requires us to slow down and think about air itself. We pass through air constantly, but we rarely consider its properties. Air is not empty space. It has substance, weight, and texture. It can be measured and predicted. When you move your hand through the air, you can feel it pushing back, offering gentle resistance. This resistance increases with speed. Move your hand faster, and the air pushes back harder. This is drag, and it is one of the 4 fundamental forces that act on an aircraft. An airplane wing has a distinctive shape. It is curved on top and flatter on the bottom. This shape is called an airfoil, and its design is crucial to flight. As the wing moves through the airflow splits. Some air travels over the top surface and some flows beneath. The air moving over the curved top surface must travel a slightly longer path than the air moving along the flatter bottom. To cover this longer distance in the same amount of time, the air on top moves faster. Faster moving air creates lower pressure. The slower air beneath the wing maintains higher pressure. This pressure difference pushes the wing upward. This upward force is called lift. It is the most fundamental force of flight, and it happens continuously as long as the wing is moving through the air. The process is quiet and natural, requiring no sound or visible effect. The wing simply rises. But lift alone is not enough. An aircraft must also overcome drag, the resistance of the air, and it must generate thrust to move forward through that resistant air. The Wright brothers used propellers driven by their engine to create thrust. As the propellers spun, they pushed air backward, and Newton's third law pushed the aircraft forward. The fourth force acting on an aircraft is weight, pulling it constantly toward the earth. For an aircraft to fly, lift must exceed weight, and thrust must overcome drag. It is a delicate balance, maintained through design and piloting skill. The Wright brothers understood another crucial principle: control. A bird doesn't simply float through the sky on fixed wings, it adjusts constantly, tilting, banking, shifting its weight to turn and maintain balance. An aircraft must do the same. The Wright Flyer achieved control through a system of wires that warped the wings, physically changing their shape. When the pilot wanted to turn left, he would shift his hips in a cradle, pulling wires that twisted the left wing down and the right wing up. This created more lift on the right side, causing the aircraft to bank and turn left, a movable horizontal surface mounted in front of the aircraft-controlled pitch, tilting the nose up or down. When the pilot pushed the control forward, the front surface tilted downward, causing the nose to drop. When the pilot pulled back, the surface tilted upward, lifting the nose. Early pilots learned to sense the air around them. A gust from the left meant compensating with control inputs. A sudden dip in pressure, detectable by the feel of the controls, meant the aircraft was about to sink. Flying became a continuous conversation with the wind, a dialogue conducted through wood and wire and fabric. Materials and craftsmanship. These first aircraft were built from materials chosen for specific qualities. Every component was selected with care, balanced between strength and weight. The pioneers of flight were as much craftsmen as they were engineers. Spruce wood formed the skeleton of most early aircraft. Spruce grows straight and tall in northern forests. When properly dried and selected, it offers an exceptional strength-to-weight ratio. The wood has a fine, even grain that resists splitting. It can be shaped with hand tools and joined with simple glues and fasteners. The Wright brothers selected each piece of spruce individually, examining the grain, checking for knots or imperfections. A weak strut could fail in flight, so every piece had to be inspected. They would run their hands along the wood, feeling for irregularities, holding pieces up to the light to see the grain pattern clearly. Ash wood was sometimes used for areas requiring extra toughness, particularly in the landing skids and areas subject to impact. Ash is heavier than spruce, but more resistant to sudden shocks. When an aircraft landed hard on uneven ground, ash absorbed the impact without splintering. Some builders experimented with bamboo, particularly for jury struts and cross-bracing. Bamboo is remarkably light and surprisingly strong. It grows in hollow sections naturally reinforced at intervals. European builders sometimes imported bamboo from Asia, valuing its combination of flexibility and strength. The wings were covered with fabric, typically unbleached muslin. Muslin is a plain weave cotton fabric, lightweight and tightly woven. Bolts of muslin would arrive at the workshop, and the fabric would be cut to patterns and sewn by hand or on treadle sewing machines. The fabric was then stretched tightly over the wing framework and secured. But raw muslin was porous and would allow air to pass through. To seal the fabric and protect it from moisture, builders applied coats of fabric treatment, a mixture of nitrocellulose dissolved in solvents. Applying fabric treatment was careful work. The liquid was brushed on in thin, even coats. Each coat had to dry completely before the next was applied. Too much fabric treatment added weight. Too little left the fabric vulnerable to weather. The smell of fabric treatment was distinctive and strong, a sharp chemical odor that filled the workshop. Wire held the structure together and provided tension to keep the wings rigid. Piano wire was preferred for its high tensile strength. The wire was thin but incredibly strong, capable of handling loads many times its own weight. Each wire had to be measured precisely and fitted with turnbuckles that allowed for adjustment. The engine components required different materials entirely. The engine block was cast aluminum, a relatively new material in the early 1900s. Aluminum was light, but could withstand the heat and stress of combustion. The cylinders were steel, as were the crankshaft and connecting rods. Bearings were often made of brass or bronze, materials that could handle rotation with minimal friction when properly lubricated. Gaskets were cut from leather or cork. Fuel lines were copper tubing, bent carefully by hand to route fuel from the tank to the carburetor. Propellers were carved from wood, usually spruce or walnut, laminated in layers to prevent warping. Carving a propeller was an art form. The blade had to be shaped to create lift, just like a wing, with the angle changing along its length. The wood had to be balanced perfectly, or the propeller would vibrate and tear itself apart. Each propeller was carved slightly oversize, then tested. The builder would shave off small amounts of wood and retest for balance and shave more if needed. The process continued until the propeller ran smoothly at full speed. The final step was applying multiple coats of varnish to protect the wood from moisture and prevent splitting. Landing gear required careful thought. The Wright Flyer used simple wooden skids, which worked well on sand but not on harder surfaces. Later, aircraft adopted wheels, often salvaged from bicycles or motorcycles. The wheels were mounted on axles fitted with primitive shock absorbers, sometimes just bundles of rubber cord. Every bolt, every screw, every metal fitting had to be considered. Steel was strong but heavy. Brass was easier to machine but softer. The builders became experts in choosing the right material for each specific purpose. The craftsmanship extended to the smallest details. Fabric seams had to be sewn with strong thread in straight, even lines. Wire connections had to be wrapped and soldered carefully. Wood joints had to fit tightly, with glue applied evenly and excess squeezed out. Nothing could be sloppy or approximate. Lives depended on the quality of the work. Tools and repairs. The workshops where these aircraft were built and maintained were filled with hand tools, most of them familiar to any woodworker or mechanic of the era. The work of aviation in these early years was hands-on, physical, and deeply personal. Saws were essential. Hand saws for cutting spruce struts to length, their teeth sharp and set properly for cross-cutting. Coping saws for cutting gentle curves. Back saws for precise cuts in smaller pieces. Each saw had its purpose, and experienced builders knew which tool to reach for without thinking. Planes smoothed the wood after cutting. Block planes for small work. Jack planes for longer pieces. The plane blade had to be razor sharp and set to take thin, even shavings. Running a plane along a spruce strut produced long curls of wood that fell away like ribbons. The smell of fresh-cut spruce filled the workshop, clean and resinous. Chisels carved joints and cleaned up imperfections. A set of chisels ranging from 1/4 inch to 1 inch wide allowed for detail work and heavier shaping. The chisels were kept sharp on oil stones, a task performed almost daily. A dull chisel was worse than useless. It could slip and damage the work or injure the craftsman. Clamps held pieces together while glue dried. C-clamps and bar clamps in various sizes lined the walls of the workshop. When gluing a wing rib or assembling a fuselage section, sometimes dozens of clamps were needed. The pieces had to be held firmly, but not so tightly that the wood was crushed. Drills created holes for bolts and wire fittings. Hand drills with T-handles. Bit braces for larger holes. The holes had to be straight and accurately placed. Builders used marking gauges and squares to ensure precision. Files smoothed metal parts and adjusted fittings. A set of files included flat, half-round, and rat tail shapes for different tasks. Files clogged with metal particles had to be cleaned regularly with wire brushes. Wrenches tightened nuts and bolts. Adjustable wrenches could handle various sizes, though fixed wrenches were preferred when available. Engine work required a full set of wrenches in different sizes. The early aircraft engines used standard thread patterns, but sizes were not yet fully standardized, so a comprehensive set was necessary. Screwdrivers came in different sizes and tip styles. Some screws had slotted heads, others had different patterns. The screwdriver had to fit properly, or it would strip the screw head and make removal difficult or impossible. Pliers gripped wire and small parts. Cutting pliers snipped wire to length. Needle nose pliers reached into tight spaces. Wire bending pliers created loops and wire ends for attachment points. Soldering equipment was crucial for electrical connections and some metal joints. A soldering iron heated over a spirit lamp or in a small forge with sticks of solder and pots of flux nearby. The work required a steady hand and patience to avoid cold joints that would fail under stress. When fabric tore, repair was a careful process. The damaged area had to be cleaned and cut back until only good fabric remained. A patch was cut, sized to overlap the tear by several inches in all directions. The patch was fabric treatment D into place, sealed with additional coats and allowed to dry completely. A well-done patch was nearly invisible and just as strong as the original fabric. Wood repairs were more complex. A cracked strut could not simply be glued back together. It had to be reinforced or replaced. If the damage was minor, a splint could be glued and bound to the strut, spreading the load across the repaired area. More serious damage required fabricating a new piece and replacing the damaged strut entirely. Engine repairs required different tools and skills. Spark plug wrenches removed the plugs for cleaning or replacement. Valve adjusters set the proper clearances. Torque had to be judged by feel, as torque wrenches were not yet common in small workshops. Carburetor work required disassembly. cleaning of tiny passages with thin wire, and careful reassembly. The fuel mixture had to be adjusted by trial, running the engine and listening to its sound, feeling for smooth operation. The workshop had a distinct atmosphere. The smell of fresh wood and fabric treatment and oil combined into something distinctive. Sawdust covered the floor despite frequent sweeping. Tools hung on walls or rested on benches, each in its place. Natural light streamed through windows, supplemented by oil lamps or early electric lights. The pace of work was measured but steady. Rushing led to mistakes. A misdrilled hole or a poorly fitted joint could not be easily undone. The builders learned patience, learned to work carefully, and check their work constantly. Aviation meets and competitions. As aviation capabilities improved, public interest grew. Aviation meets became popular events, drawing large crowds and significant prize money. These gatherings advanced aviation by encouraging competition and innovation. The Grande Semaine d'Aviation, held at Reims, France in August 1909, was the first major international aviation meet. Organizers offered substantial prizes for speed, altitude, and distance. Pilots from several countries participated. The meet took place at a military training field outside Reims. Grandstands were erected for spectators. Tents housed the aircraft and served as workshops. Each team had space to make adjustments and repairs between flights. The atmosphere combined carnival and serious competition. Crowds arrived by train and automobile. Ladies carried parasols against the sun. Gentlemen wore suits and hats. Everyone came to witness the miracle of flight. Henri Farman won the distance prize by flying 112 miles in just over 3 hours. He circled the course repeatedly, the engine droning steadily while crowds cheered each lap. When he finally landed, he had demonstrated that aircraft could sustain flight for meaningful periods. Glenn Curtiss won the speed prize by covering 20 kilometers at an average speed of 47 miles per hour. His aircraft was noticeably faster than competitors, benefiting from his experience with engines and his focus on minimizing drag. Hubert Latham achieved an altitude of 508 feet, winning that prize. Climbing was a slow process, requiring time and fuel. He circled upward in a gradual spiral, the aircraft visible as a speck against the sky until he reached his maximum altitude and glided back down. Louis Blériot attended as a celebrated figure, having crossed the channel just weeks earlier. He didn't win major prizes, but delighted crowds with demonstrations of his aircraft's maneuverability. The week included some crashes, though none fatal. An aircraft might ground loop during landing, collapsing a wing. Another might porpoise during takeoff, bouncing hard and damaging the landing gear. Crews quickly made repairs and flying continued. Other meets followed Reims, Brescia in Italy, Doncaster in England, Los Angeles in America. Each attracted top pilots and showcased the latest designs. Prize money reached substantial sums, encouraging professional pilots to develop their skills. These competitions served several purposes beyond entertainment. They demonstrated aviation's progress to skeptical publics and government officials. They provided opportunities for builders to compare designs directly. They created a community among aviators who shared information and techniques. The social aspect mattered too. After flying ceased for the day, pilots and builders gathered to discuss their experiences. They compared notes on engine performance, control responses, and handling characteristics. Ideas spread through conversation. Women attended these meets, both as spectators and occasionally as pilots. Their presence challenged assumptions about gender roles. When Raymond Delaroche or Hélène Dutrieux flew with skill equal to male pilots, it was difficult to argue that women lacked the ability to fly. Meets also attracted potential customers. Military observers attended, assessing whether aircraft had military applications. Wealthy individuals considered purchasing aircraft for sport. Newspapers sent reporters and photographers, spreading aviation news widely. The competitive element drove innovation. Builders wanted to win prizes, which required superior performance. This encouraged experimentation with new configurations, more powerful engines, and refined aerodynamics. Progress accelerated through competition. Safety gradually improved as pilots learned techniques and aircraft designs matured. Early meets had alarming accident rates. By 1910, while flying remained dangerous, pilots better understood the limits of their aircraft and how to avoid situations likely to cause crashes. Weather, wind, and flying conditions. Early aviators were intimately connected to weather and atmospheric conditions. They had no instruments to measure wind speed or turbulence, relying instead on observation and experience. The best time to fly was early morning, just after sunrise. The air then was typically calm, with minimal thermal activity. The sun had not yet heated the ground enough to create rising air currents. Wind speeds were usually lowest in the hours just after dawn. Pilots would arrive at the field before sunrise, preparing their aircraft in the dim light. As the sun rose, they would watch flags and tree branches, observing wind direction and intensity. If conditions looked favorable, they would fly. Midday was treacherous. Solar heating created thermals, columns of rising air that could lift an aircraft suddenly or drop it just as quickly. These invisible currents were impossible to predict. An aircraft flying straight and level might suddenly rise 20 feet, then drop 30, throwing the pilot against restraints if any were fitted. Late afternoon sometimes brought a second calm period, especially in summer. As the day cooled, thermals weakened. If the wind remained light, evening flights were possible. The slanting light made the landscape beautiful, though shadows could hide obstacles on the landing approach. Rain was absolutely prohibitive. Water added weight to the fabric wings, reducing lift. It made wooden controls swell and bind. Visibility dropped to unacceptable levels. Pilots sheltered in hangars during rain, waiting for clear skies. Wind direction mattered greatly for takeoff and landing. Aircraft had to take off into the wind to maximize airflow over the wings and generate sufficient lift. Landing required the same approach, touching down while moving into the wind to minimize ground speed. A grass field served as the ideal flying surface. Grass was smooth enough for wheels or skids, soft enough to cushion hard landings. Pilots learned to read the grass, watching how it moved to gauge wind direction and speed. A light breeze would make grass ripple gently. Stronger wind would flatten it in waves. Temperature affected engine performance. Cold air was denser, providing more oxygen for combustion. Engines ran stronger in cool weather. Hot days reduced engine power by several percent, which could mean the difference between successfully clearing trees or striking their branches during takeoff. Altitude compounded temperature effects. Higher altitude meant thinner air, less oxygen, less power. An aircraft that could carry 2 people at sea level might only carry 1 at 2,000 feet elevation. Clouds were navigational hazards. Flying into a cloud meant losing all visual references. Up and down became uncertain. Without instruments, pilots could become disoriented within seconds. All early flying was done in clear air, staying well away from clouds. Fog was similarly dangerous. It could form unexpectedly, rolling across a field and obscuring the ground. A pilot returning from a flight might find his landing field invisible beneath a white blanket. Smoke from factories or fires provided useful information. Smoke showed wind direction at various altitudes. If smoke at ground level drifted east, but smoke at 500 feet drifted northeast, the pilot knew wind direction changed with height. This information helped plan approaches. Birds were observed carefully. If birds struggled to fly or landed suddenly, conditions were deteriorating. If birds soared effortlessly, thermals were active. Watching how birds handled wind gave pilots clues about what their aircraft might experience. Winter brought special challenges. Cold temperatures helped engine power, but made pilots numb and slow to react. Leather gloves protected hands, but reduced sensitivity on controls. Heavy clothing was necessary, but restricted movement. Snow covered landmarks and made distances deceptive. A snow-covered field looked perfectly smooth but might hide furrows or rocks. Landing on snow was risky, as the aircraft might nose over if the skids or wheels dug in. Summer heat created its own problems. Pilots wore light clothing but still suffered in open cockpits under the sun. Dehydration affected judgment. Long flights in summer heat left pilots exhausted. Storms were visible from the air and pilots gave them wide clearance. A line of dark clouds on the horizon meant turbulence, strong winds, and possibly lightning. No pilot deliberately flew near storm systems. The low altitudes at which early aircraft flew kept them in intimate contact with the land. At 200 feet, a pilot could smell fresh-cut hay, hear dogs barking, see faces looking up. The connection to the earth below remained strong. The years from 1903 to 1910 represent a unique moment in human history. Flight transformed from an impossible dream into demonstrated reality. The pioneers who made this happen were not superhuman. They were bicycle mechanics, wealthy sportsmen, engineers, and dreamers who shared a vision and the determination to make it real. Their aircraft were simple constructions of wood and fabric and wire. By modern standards, they were fragile and dangerous. Yet, they flew. They lifted humans into the air and brought them back safely. They proved that the dream was achievable. The lessons learned in those 7 years shaped all aviation that followed. Control surfaces, wing design, engine development, and piloting techniques established in this period remain relevant today. Every aircraft that flies owes something to those early pioneers. But beyond technical achievements, those years represented something more fundamental. They demonstrated human capacity to solve seemingly impossible problems through patient observation, careful experimentation, and persistent effort. The Wright brothers spent 4 years observing, testing, and refining before their first successful flight. Others invested similar time and energy. The pioneers accepted failure as part of learning. They crashed repeatedly but rebuilt and tried again. They shared information, building collectively on each success and learning from each setback. Progress came through community effort as much as individual genius. The pioneers of aviation discovered not just how to fly, but that flying could be peaceful. A meditation on movement and balance, a conversation with wind and gravity, a way of seeing the world from a new perspective while remaining intimately connected to it. And so, we leave them there in those early days of flight, circling slowly above summer fields, exploring the lower reaches of the sky with wonder and careful attention, finding joy in motion and peace in the simple fact of being airborne. The wooden propeller turns steadily, the fabric wings hold firm against the air, the wires sing their quiet song. Everything is exactly as it should be. If you enjoyed this journey, please consider liking this video and subscribing to the channel. Share your thoughts in the comments below. Rest well. Good night.